So we've just seen that to evaluate integrals around a closed loop of a function which contains singularities inside the loop, we need to find the residues of those singularities. So just to remind you, the residue is simply B1 in the Laurent series. So where's the Laurent series? Okay, so the Laurent series residue just means this value B1. So we're now going to look at techniques for finding B1. Now, the most obvious thing, the obvious technique, is actually just to write down the Laurent series. I say just. This can be a bit of an effort, and it's actually normally not the fastest way to find the residue, but we'll look at it's the most direct method, so we'll look at it first. So in all of the following, we're going to be considering finding the residue of a function phi z at a non-removable singularity. So remember, removable singularity we defined as one where actually it's sort of not really a singularity in the sense that the limit exists as z tends to z0 and it's finite. So we're always going to say the singularity is at z equals z0. So the most direct method is just to write down the Laurent series for phi z about z equals z0 and find the coefficient of 1 over z minus z0. Now this is easy to do if z0 happens to be 0. Otherwise it's a bit more difficult, as we will see in the example. My recommendation is to save writing. It's best if you define a symbol to mean z minus z0. So we're going to use delta. And then the residue is the coefficient of 1 over delta. That's what we have to find. Okay, so in this example, we want to find the residue of sine z over z minus I squared at z equals I. Okay, so we need to expand. Well, the z minus I is good. That's okay, because that's already in the form delta. So we're going to replace this by delta squared. But the sine z we need to write in terms of delta. Okay, so we define delta as z minus z0, so delta is z minus I, or z equals delta plus I. So substituting that into there, we've got sine z is sine delta plus I, just using the normal formula. That gives us this. And then we just use the expansion of sine delta. So sine delta is the usual formula, delta minus delta cubed over 3 factorial plus and so on. Cos I, well, remember cos I z is the same as cosh z. So in this case, z is 1. So cos I is actually just cosh 1. Similarly, with cos delta, we expand in the normal way, and we've got sine I. So remember, sine I z is equal to I shine z. So it's I, and shine z is 1. So we've got shine 1. So that's sine z. We then just need to divide sine z by delta squared. So if we divide all of this by delta squared, we then just look for which term is multiplying the 1 over delta. So obviously there's only one term which is going to give us 1 over delta. When we divide by delta squared, this is going to give us 1 over delta. Obviously delta divided by delta squared is 1 over delta. And the coefficient of that is cosh 1. So that means the residue is cosh 1. Okay, so next we're going to look at simple pole methods. So these methods, I should stress, they're called simple pole methods because they only work if Z0 is a simple pole. Now, in this previous example, Z0 is a pole of order 2, obviously, because you've got Z minus I squared on the bottom, and this is not 0 when Z equals I. So for example, these methods we're going to show now wouldn't work for this example here. Okay, so if Z0 is a simple pole, then one way of finding B1 is simply to multiply phi z by Z minus Z0, and then take the limit as Z goes to Z0. Okay, so it's fairly obvious why that's true. All we need to do is multiply the Laurent series by Z minus Z0, so that's 2.8. Where's that gone? Here. So if you imagine multiplying this by Z minus Z0, what's going to happen? And then letting Z tend to Z0. So if we multiply this by Z minus Z0, all of these things are going to have Z minus Z0, which as Z tends to Z0 will give you 0. If I multiply this by Z minus Z0, then I just get B1. The Z minus Z0 cancels. And if it's a simple pole, B2, B3, etc. are already 0. So we just get left with B1. So it's easy to see why that method works. So this is really pretty much a direct method. It's not quite as direct as obtaining the Laurent series, but it's pretty close. Okay, so suppose we can write phi z as pz over Z minus Z0 times R, where P at Z0 is not 0 and R at Z0 is not 0. Therefore, phi Z has a simple pole at R0. Then if we multiply both sides by Z minus Z0, we end up with the result that the residue at phi Z0 is just P at Z0 divided by R at Z0. So this is really using this in practice. So basically what we're saying is that if you see this factor on the bottom, Z minus Z0, and you realize that causes it to be a simple pole, basically because this is not 0 and this is not 0 when Z equals Z0, so it's therefore a simple pole, then all you have to do is get rid of that factor and then evaluate this at the P divided by R at Z0, and that gives you the residue. So this is quite a direct method. In practice, it's still not the simplest, or it's not the fastest method. Might be simple to think about, but it's generally not the fastest method. The fastest method is the following. So this takes a little bit more effort to actually derive, but it's actually very quick to actually use. So this is the method I strongly recommend that you use unless there's a good reason for not using it. Remember, it only applies to finding the residue of a simple pole. Right, so if phi, your function can be written as P divided by Q, where essentially at the singularity P must not be 0 and is also finite, and in order for you to get the singularity you must therefore have to have that Q at Z0 is 0, then the residue is simply P evaluated at Z0 divided by Q dashed evaluated Z0. So very, very nice, simple formula. Okay, so why does this work? Well, we go back to this general expression, which will always work for simple pole. Okay, so the residue is the limit of z times z minus z naught times phi as z tends to z0. And now we've said that phi can be written as p over q. Okay, we replace the phi by p over q. Then the residue is this, limit of z tends to z0. Then we apply L'Hopital's rule. Well, basically, we know we can apply L'Hopital's rule because this is going to tend to 0 as z tends to 0 because you've got z minus z0. And we've already said that q has to be 0 when z equals z0. So we've got 0 divided by 0. So we can apply L'Hopital's rule. So L'Hopital's rule, remember, means you differentiate top and bottom. So if we differentiate top and bottom, what do we get? Well, obviously, differentiating the bottom just gives us q dashed. Differentiating the top, what does that give us? Well, differentiating the z minus z naught will just give us p, and differentiating the p will give us p dash times z minus z naught. Then we take the limit as z goes to z0. The z minus 0 term, so this is basically going to give us z minus z0 times p dashed plus p plus p. So because we're looking at the limit as z tends to z0, the z minus z0 times p dash term will vanish, and we just get left with p of z0 divided by q dash of z0. So question 16 is not amazingly important. You can have a go at it. Show why 220 should not be used if p at z0 is 0. The clue is to look at the proof of this and see where it fails. Okay, so I'll stop there and continue with the example in the next lecture.